the entry and exit tone. So if people join in, you don't get the doo-doo. So go to click participants, file, share, whatever, and then participants, and then untick the entry and exit tone.
Oh, got it.
Okay, yeah, that sounds great. Hi everyone.
Hello.
How are you guys doing?
Good. Oh wait.
Doing good.
Maybe sometime soon we should have these meetings in person, so it's less awkward. Yeah. Let me see. Wait. Kin, I wanted to ask you, are you still working with Dr. Chacheski?
Yeah.
Okay.
Actually, I didn't. I thought you were going to ask him to be the moderator.
Wow.
Because I just told him I'm going to present and asked him for the comment on the slides. So I assume he will attend this meeting.
I hope so.
Yeah, I can't 100% sure, but yeah.
Yeah, that's fine. Cool.
Yeah.
We hope he will join.
Yeah, just don't ask the question that are too difficult.
We'll ask you the questions that we are interested in knowing.
Hey, let me speak up. Is this for
Oh, hi.
grad students or faculty as well? I'm the only faculty. Maybe I should bail out.
No, please. No, please stay. This is for everyone, including faculty.
Yeah, we have Dr. Famian also with us. So
I just saw him a minute ago outside. He might have been, yeah, they were going to the FETSA Center. I think I know why. But okay, I'll hang in. But if I'm the only faculty, oh, there's Mike. Yeah. Okay, good.
All right, so do I start now?
Okay, let's give it 30 more seconds, and then I'll do the introduction, and you can.
Oh yeah, sure.
Yeah, you can start sharing your screen.
All right.
And see if that works.
How do I hide this thing? There's something on the top.
Yep. Oh, so you using, man, we can't read anything there.
Yeah.
Okay. All right. Okay. I guess you can click record, then I can.
Oh, I already do.
Is this already recording?
Yeah.
Okay, let us start. Welcome again, everyone. Thank you for joining for another session of the Physics Journal Club. The purpose of this club is for us to interact with ongoing research in physics so we can get inspired, learn what's going on, and build also our skills to extract information from literature and stuff like that. And so our speaker today, we're excited, Tam King, if I say that correctly.
Yeah,
He'll be talking to us about how to apply machine learning to determine the impact parameter in nuclear physics experiment. Okay, King, go ahead.
Okay, so first of all, thanks for everyone to join this meeting. So I will be talking about how to apply machine learning to this to determine the impact parameter in a heavy ion collision experiment. So here's my outline. So first of all, I will talk about some background knowledge about impact parameter, and then I will move on to a one-slide introduction to machine learning. But I won't go too deep into the the actual algorithms used in the machine learning. But I will just share the idea of the machine learning applied to this paper. So after that, with this knowledge developed, we can, I will go to the method used in this research paper. And finally, I will present the results and summary. So first of all, what is impact parameter? So I think all of us here should know about this already. It is the perpendicular distance between the projectile and the target. So you can have a look at the figure on the left-hand side here. So you can imagine these two balls as two nuclei. The purple one will move to the right and the green one will move to the left. So the perpendicular distance here, I label it B here, is the impact parameter. So if the value of B is small, then it would be a head-on collision. If the B is large, that I will call it a peripheral collision. So the importance of determining the impact parameter accurately is that if you have different value of B, then it will lead to different kind of physics. So let's focus on the right-hand side of the figure here. So if the collision is somehow central, which is a head-on collision, then what you expect is that there would be more participants region here. So you see the target spectator here refers to the particles that are not really participated in the collisions. So you can somehow imagine these two nuclei as two cars. So if they smash into each other directly, then you expect everything exploded. So it will be more. There will be more participants. But if the two cars just barely slide each other, then you expect not many things happens here. So the projectile spectator here will be smaller. Okay. So if the value of B is not determined accurately, then it will become very difficult for you to analyze the data because, you know, two different physics phenomena will happen together in your data and it will be hard to distinguish. So the problem in experiment is that this impact parameter is not directly measurable. What I mean is that you cannot put a ruler to the nuclei and then just measure it. This is just impossible. So one of the conventional methods to determine the impact parameter is to use the charge particle multiplicity. So we can look at the figure here. The x-axis is the charge particle multiplicity, and the y-axis is the actual impact parameter. So as you can see that as the impact parameter decrease, which means that it becomes a head-on collision, just like two cars, they collide to each other directly, then everything exploded. So there, what you expect is to see that there will be more charged particles produced in this collision. And if the collision is peripheral, then there will be less charged particles. So use this relation, somehow you can model the relation between the charged particle here and the impact parameter. But the problem is that at the central collisions here, you see the uncertainty is actually very large, about 2 Fermi here. And you see the error bar is actually covering the mid impact parameter region and the central region. So it will be difficult for us to analyze the data if this parameter is not determined accurately. So the resolution is to use machine learning. So in this figure, the x-axis is the actual impact parameter, and the y-axis is the predicted impact parameter using the machine learning method. So here we know that this actual the true impact parameter here because these data are generated by simulation. So we can have a comparison here, and you see that this is from a previous study, and it has already been shown that the accuracy of determining impact parameter using machine learning is much better. And the uncertainty is just 0.16 Fermi and 0.08 Fermi using different algorithm, different machine learning algorithm as compared to the conventional method. But this is already been done. So the focus of this current paper would be how to apply this machine learning method on experimental data. Okay. So now I will briefly introduce the idea of machine learning. So according to Wikipedia, this is just the Wikipedia definition I found. So it is the study of the computer algorithm that can improve automatically through experience and by the use of the data. But this is quite an abstract idea. But I will explain using this figure. So the idea is actually quite simple. So first of all, of course, you have to prepare some data, a large amount of data. And you will split this into two sets of data. The first set is called the training data, and the second set is called the test data. So I figured there is a, so I think it's useful to think that the training data is some of the data that you have already gathered. For example, you want to predict the price of a stock in next year. So the data available to you now would be all the stock price up to today. So this would be the set of the training data. Okay. So after you obtain the training data, you apply this data to some modeling. Maybe you perform a simple linear fit. This is the simplest model. And you, of course, you fit the data, and then you can, I mean, after 1 year, you just find out the stock, the price of that stock would be at certain value. So that would be your test data. So you, by now you can compare this model result with your training, with your test data, because you already predicted the value of the stock 1 year after 1 year using this model. So you see that in this method you can just compare the difference, the simplest model validation here. But if what we want is that if this error delta y here is small, that means the model is performing quite good. But if it is not good, that means maybe the model is wrong. So you go back here, and then you maybe use another model or other method to do the modeling. Okay, so this is the idea of the machine learning. So with this knowledge developed, we can talk about how it is used in determining impact parameter. Okay, so first of all, we still need simulations. And the reason is that if we just use the experimental data, and what we have is just all the particle energy, particle momentum, blah, 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 other observables, but we don't have the impact parameter. So in this case, we just can't determine, I mean, we can't fit a model to here because we simply don't have the impact parameter data. Okay, and the solution is to do simulation, because in the simulation, we know the actual impact parameter here. In fact, this is one of the input parameter you put into the simulations. So we know this value exactly. So in the simulation, what you also know is the charge particle multiplicity, the mass, momentum, energy, angle, or other observables of the output particles. And here is one of the examples that shows the relation between the actual impact parameter and the charge particle multiplicity. Okay, so but we call that our goal is always to predict impact parameter using the experimental data. So in the previous simulation, there are no detector involved. I mean, if I simulate the data based on just that simulation, what the data I obtain will be in general quite different from what you obtain from experiments. So the reason as follows. So if I simulate the data with, for example, the experimental setup taken into account, then I will, have to build a Gen 4 simulation, and then I specify the detector position, detector coverage, or other stuff. So, but in real experiments, it is never possible to cover all angles, because we have to have something to mount the detector. And also in real experiments, there is always some problems in your detector. Maybe a small part of your detector is not functional within a period of time. So there are many aspects that you need to take into account. But if you are just using the previous simulation without detector considered, you can always record the particles, momentum, energy, everything, no matter which angle it is produced. And by the same logic, without detector considered, you can always record particle with any energy, even if the energy of the particle is 10 GeV, okay? That you can still record it. It is just not physical, but in principle, it can still be recorded. But in real-life experiments, this detection energy range is limited by the detector thickness. So if a particle has a very high energy, in principle, it can punch through the detector and the detector never see this particle and you can record nothing. So there's a many difference between these data generated by with perfect detector and in your real-life experiments. And also this is also, we have detector efficiency because the particle also will interact with the detector. I mean, the material inside the detector. But if we use the previous simulation without detector, then the efficiency is always 100%. Okay, so now just let me summarize the data sets available for us to use. So first, we have the original simulated data with this perfect detector. What I mean is actually there is no detector involved in the simulation, right? And also we have another set of data, which is the simulated data with the real-life detector response taken into account. So the author will split these two sets of data into two cases, just as what we have discussed. So for the training data, we have the data with perfect detector and the data with realistic detector response. And this is the same for the test data. We split it into two cases. So now we can apply the method of machine learning on this data. So for the training data, we can just have a simple model. What I mean is that you have to input a function so that if you are given this, for example, charge particle multiplicity and maybe other observables, then this model will give you the value of impact parameter. Okay, so this can be done within the training data, using the training data. And in the test data, we can quantify the performance of this model by evaluating the bias, which is defined by just the difference between the predicted value using the training data and the actual impact parameter, because we already know that it is the input parameter of the simulation. So the author used 3 tests here. So the first one is that we first train the data with perfect detector, so that then we test the results with the data with perfect detector again, and then we can also train the data with realistic detector response, and then we test the data with the same thing. But finally, this is something special here. We can also first train the data with a perfect detector, and then we can test this model on this data set with realistic detector. Okay, let me just summarize the steps used in these models, which is maybe a little bit tedious. So first of all, we have 2 possible sets of data. The A part, the first one is that we have actually no detector or perfect detector in the simulation. And the second one is the data with detector response. After that, we split this each of these data set into 2, in the training data and the test data. So what I really means here is that maybe you have 10 observations in part A, so you can just take 5 observations as your training data and the rest of the data as your test data. Okay. And finally, not finally, and next step is just to fit your model. So for example, this is just the definition here. What I mean is that here you can consider the predicted value of the impact parameter as a function of the other observable you can obtain from the simulation. So using this model, you can predict the value of the impact parameter. So finally, we can test the performance of the model by evaluating the bias using the test data. So there are 3 cases, and the most important case, I mean, the first 2 cases are very obvious. You just train the data with perfect detector and test with perfect detector, and realistic detector and test with realistic detector. But the final case is that you train the data using the perfect detector and test with realistic detector. And there's a reason to do this, because naively thinking, you will think that this should not be done because it doesn't make sense, because these are 2 different data sets. So even though if the modeling is quite good in the perfect detector, there's no reason to apply it to the realistic data. So I think the reason they do this is just because I mean, so if I train the data with perfect detector and it turns out the bias is very low, if I test it with realistic data, that will be a great thing to do, because the computational cost for training with perfect detector is much smaller. So this is the reason I think why they're doing this. So now I will present the results. Okay, so first result I want to present is that this case is actually not good. So in this table, this column is the predicted impact parameter using the model, and the second column here is the performance of the model. So this label here, what I mean is to first train the data in perfect detector and then test with perfect detector, and then similar logic here. So what we observe here is that the bias in these 2 cases is actually very low. So this is quite a satisfactory result. But the problem is that if we train with the perfect detector first, and then we test the model using the data with realistic detector response, then you see that the bias is actually extremely large compared to the first 2 cases. So the conclusion here is that this case is actually not good. So we can simply forget about this case. If we want to predict the impact parameter using experimental data, we have to do simulation with the detector response considered. Okay, so the second result I want to present is that in general, the method of the machine learning is much better compared to the conventional method. So this is the figure. The y-axis here is the bias, so which quantify the performance of the method of machine learning. And the x-axis here, I believe it is the actual impact parameter used in the simulation. So first of all, I want you to observe the overall trend here. Oh, by the way, this line here, what it represents is the impact parameter predicted by the conventional method using charge particle multiplicity. And the red circle here is you first train with the detector response and then test with detector response, and the blue star is without the detector response. So the first observation here is that in general, the bias using machine learning is much smaller than the one using multiplicity, right? Because what we want is that the bias to be 0. That means your prediction will be exactly equal to the actual impact parameter, which is good. So you see, these 2 curves is much closer to 0 compared to the black line. So we expect, so we see that the machine learning is actually much better. So the second observation here is that the prediction using machine learning is actually not quite good in this region, around b equals to 3. So according to the author, the reasons for this worsening is that it's because of the physics used in the model. So so in the central collision, so the physics in the model is dominated by the nuclear collisions. Okay, and large impact parameter, which is peripheral collisions, all the physics is dominated by the mean field effect. So that means it's just the FH motion, the FH effect of the potential of this pair interaction of the particles. But in this intermediate region, I think the physics is somehow a combination of these two effects: the nuclear reaction, actually the nuclear force and the mean field effect. So the model is not quite good in determining or simulating this effect in this region, because with two effects mixed up, then the calculation will be much more complicated. Because as you see, the mean field potential, you can solve it exactly, but you can't solve it exactly with something else added into your Hamiltonian. So I think this is the reason why the prediction is worsened in this intermediate region. Okay, and finally, we also expect to see that the prediction is worse if we consider the detector response here, because obviously you will have more error bar, because if you incorporate the detector response in your simulation, then first of all, the simulation inside the detector will cause some error, and you have some many corrections to do if you have a detector. For example, you have interactions inside your detector, and you have some kind of efficiency issue that can also cause an error. So in general, we can see that the performance of the red circle is a little bit worse than the blue star here. But in general, it is still quite good compared to the previous results. So the next result I will show you is that is this graph. We just compare the machine learning results with the experimental data. So previously, what we were doing is that we used the simulated data with detector response considered in your simulation. But in this case, we finally apply the model used in the machine learning to the experimental data to predict this impact parameter. So the y-axis here is the predicted impact parameter using the conventional method, and the x-axis is the impact parameter predicted by machine learning. So you see that this red line is just a reference for perfect prediction, but we can see that the general trend is that the results are in great agreement, I mean, in general. And also you can see that the method of the multiplicity, it cannot predict impact parameter larger than the 7.8 Fermi meter. So the reason is because, maybe let me just move on to this slide. The reasons for this is that they use this equation to predict the impact parameter. But there is a hard, what do we call the maximum value of the impact parameter predicted here. So anything beyond this value, it will be set at 0, which is represented by this green line in this figure. But there is no this limitation in machine learning. So the prediction from machine learning is that at high impact parameter, the distribution is actually quite smooth. And this is more physical because you don't expect to see a hard wall here for the impact parameter. So the final result I want to present is the this reaction plane angle resolution. So this is an observable that we expect to vanish in central event because okay, so this phi m is actually the measured angle, and this phi r is actual angle of the particles. So we expect it to be 0 because we expect the, so if the collision is central, that means they collide with each other. Then what you expect to see is that the particles produced will be shooted into different direction. But since the collision is central, it is symmetrical. So we expect the angle would be like symmetrical above 5. So this is why we expect this observable to be 0. So in this figure, the x-axis is the predicted value of the impact parameter using these two methods, and the y-axis is the value of this observable. So using the conventional method, the impact, this observable is very large. So this is not a good prediction because we expect it to be 0. But by using machine learning, we can kind of push it to the closer limit. So it kind of works better than the multiplicity. So in summary, the author has successfully simulated and trained the data with a realistic detector response considered. And this is quite remarkable because the work of incorporating the realistic detector into simulation is actually quite tedious because you have to build a very large simulation using Gen4 with, it would be actually quite hard to incorporate the model to the detector in terms of coding. That's my opinion. But also in general, the prediction using the machine learning is quite consistent with what we obtained previously. So this is a evidence that what we are doing is actually correct. We are on the right track. And also as long as the training data and the testing data is consistent, which means that if we train the data with detector response and test the data with detector response again, then the error bar would be small. Just make sure that you don't train the data with a perfect detector and then test your data with detector response. That would make no sense. But anyway, the error bar is quite small. And it is so that we can use machine learning to predict impact parameter much better than using the conventional method. And this would be important to better analyze your data, because now you can distinguish the region, and it will be really a big deal. Okay, I think that would be all.
Oh, thank you very much, Kin. This was a very, very good talk.
Yeah, maybe I'm moving too fast because.
Oh no, I think it was perfect timing. It was perfect timing.
Okay.
I see Dr. Chacheski joined us. Thank you. And so hopefully he will help us as we ask questions and help moderate the Q&A session. Okay, anybody who has questions, the floor is now open. Any questions for Kin? Okay, I have a few questions of my own. I'm not sure whether you'll be able to answer them. It's concerning.
I'll try.
It's concerning the machine learning algorithm, the Light GBM.
Light GBM, yes.
Yeah,
okay.
And I saw one of the figure you showed that when you compare it to the convolutional neural network, it has a lower bias. There was one of the the previous one, yeah, that one. Yeah, and so my question was in a sense, my understanding of this gradient boost algorithms is that they follow some decision tree.
Decision tree, yes.
Yeah, and so I was just wondering if you can say a little bit more. How does that work? And
okay, yeah, I can say a little bit about it. I'm not okay. I don't fully understand the concept, but I know a small part of the idea. So in this Light GBM algorithm, so they use a technique called the decision tree. So the idea is like this. So for example, you have a, so in our example, we want to determine the impact parameter using maybe charge particle multiplicity. Let's say I just want to determine the impact parameter using two observable X and Y. So if I have X and Y, I can predict the impact parameter. So what we do in decision tree is that you first plot the graph y over x, and then actually we should start with this. For x, we can split this into, for example, two regions. So if I say that if the x is smaller than 10, then I move all the data to the left-hand side. And if x is larger than 10, I move all this data to the right-hand side. So this is one branch. And then for each of these cases, maybe I consider x2 now. x2 now, if x2 is smaller than, I don't know, some value, and then you move in all the data to the left-hand side. And then if it's larger than 10, larger than some value, and I move it to the right-hand side. So, but in our case, we have too many observables. So actually, we have 7 observables used in determining the impact parameter. So, like for the root of the tree, you will have all the data, and then in the next level, in the next branch, you split the data using the first observable. Okay, and then in the second branch, because now you split into 2 regions, so now you have 2 regions in this level, and then for each of these regions, you further split the data using other constraint of other observables. Does it make sense?
Yeah.
So actually, it would be better to have a picture because it's quite hard to explain like this.
I was thinking you can use annotate if you know how to use that. You can annotate and draw things on the screen. I think all the people who were teaching during COVID know how to do that.
I really don't know.
I think you go to more options. Maybe there's something that says annotate.
Do I have to first stop sharing?
No. You can. Yeah, you can keep sharing screen. Maybe to see if anybody else has questions.
Annotate. Okay, I see.
Then you can draw on the screen, and then things will appear.
Draw on the screen. Oh yeah, great. Got it.
Okay.
Yeah.
Anyone
my
else
screen?
with the question? Yeah, we can still see your screen. Yeah.
Okay.
Can you hear me?
Okay, good. So, so let's say the impact parameter.
I was going to say someone else has another question. Maybe can we take that question?
Sure. Yeah.
Can you hear me? Can you hear me, Kin?
Yeah.
Yes, we can.
Okay. So, like I had, first of all, on your slide 10, I was interested if it is a theoretical plot or
this one?
Yeah, this one. Which plot?
Okay, so
is it? Like,
let me just put it into full screen mode first. Okay. So what's your question?
So is it like a theoretical plot or an experiment?
This one?
Yep. So it is coming from like some simulation, or is it like
yes?
experiment?
What I want to show you is that this is one of the example that the data you can, the observable you can obtain in a simulation. So if you want this simulation, so I input, for example, I want calcium chloride with calcium. So this is my input, and I also input the actual impact parameter. Then after you run this simulation, it will give you the because in a collision experiment, then the particles will fly to everywhere. So what it gives you is the mass, momentum, energy, angle, or other features of this particle. And here I'm plotting the 2D histogram. So for each of the events, I have the actual impact parameter and the number of charged particles produced in this event. So for each point here is one event, and the color here means how many entries. Does it make sense?
Yep, makes sense.
Okay.
So second thing was like you explained there are 3 cases of training and testing data.
Yeah.
So there could be 4th case as well, training with realistic data and
that's
testing
right,
with
yeah,
perfect.
But
so
but
is it
that
like
doesn't Yeah, this is a good observation. So so the 4 cases that you first train this and then test with this, right? But this is not worth doing it because if we train the data with realistic detector response, it already costs too much time. And I mean, this one is also not making sense. But we want to test, I think they want to test it because if you train the data with perfect detector, then it costs less time.
Okay, yeah.
Do you see the point?
Yeah, makes sense. With more data, we can have more training.
Sorry?
Like with perfect detector, we can have more training. Maybe that's why.
Yeah.
Okay, makes sense. Last thing was this cos equation. I could not understand how the very last equation you showed. It was like cos phi m.
Oh, okay.
Phi r. Yeah. So does it mean phi m minus phi r equals 90 degree? Because it is like 0. So this is what I am thinking, that cos 90 should be 0. So this is some.
So actually, I forgot the exact definition of this angle, but you can consider this as just a measure in the measure of the kind of like the solar angle. So actually, let me just check the definition.
It is reaction, the plane angle. This Q, this phi r is the reaction plane, and the m is the measure.
Oh yes, yeah. So I think the idea here is that if the impact parameter is 0, that means everything is kind of symmetric, right?
Okay.
So I think the angle will just be like this.
Yeah. Okay, makes sense. Okay. Yeah. All right. Thanks.
Thank you. Anyone else with some questions? Thank you, Ken. You're doing very well.
Oh, thank you.
Anyone?
Ken,
Yeah.
can you go to slide 17?
17, this one.
Okay, here I'm a little confused with this picture shown here.
This figure?
Yes, I mean, if you look the lower value of impact parameter, right, and your actual multiplicity calculation and your machine language application, they don't agree, right? So the black solid line and those bullets.
No, this. Oh, I see. So this is the bias. This is not the actual impact.
No, I mean in x-axis it's the impact parameter, right?
Yes.
And if you look towards the lower impact value, like either 0 or in between 0 and 1, this bias is greater, right?
Yes. Yeah.
And that means can you use this ML machine learning in central reaction, because lower the value of impact parameter, that means
Yeah. This is a very good question. So the reason that first of all, I think that you can still use it for central events, because I mean the error is actually smaller than before. So it is a better method. But the reason why the error bar here is large is because actually the error in small impact parameter and the large impact parameter is large, because I think this is related to the numerical issue in the simulations, because I think in the simulation you have to somehow build a box, like, because you can't just simulate the whole world. You just have to assign the size of the box as your world. For example, just maybe 10 to, so here is 10 to 0 to 10 Fermi. So, but at the edge of this box, the simulation has some numerical issue. So the prediction will be not as good.
Okay.
Great.
Yeah,
I,
this is
I
the
have I,
yeah.
I have one question. Maybe it's a personal question. Are you actually doing this machine
No, I'm
learning
not.
algorithms? Oh, okay. Okay. I was gonna say if you are, I'll be visiting you soon. It's quite interesting.
I'm interested in this, so I'm also going to take the machine learning course next semester.
Oh, okay.
Yeah.
That sounds
yeah,
good.
I will learn these things later.
Okay. So now we have about 5 to 10 minutes for to take the quiz. I send the link in the chat. And so the prize for the quiz it's a book. And I do want to say, if you get less than 2 out of 5, you may not get the book. You at least get like 3 and above. At least that should be fine. Yeah, and Dave has won twice in a row, and so
Oh,
yeah,
nice.
we encourage everyone to take the quiz, including the faculty members, but you won't be eligible for the prize. But yeah, please do take the quiz, and yeah, it will be just next 5 minutes. And so maybe I can ask more things to you, Kin, while
Yeah, sure.
we wait. Yeah, this machine learning is quite interesting. I actually took a summer class on quantum machine learning, and the idea there was they were kind of figuring out binary problems where you have to find out a decision boundary,
Yeah.
whereby if your data is living in some space that is, multidimensional.
Yeah,
And so the idea, what they do is, if you can't find a good decision boundary that separates your data into 2 classes, what you do is you take your data and map it into a higher dimensional space, and whereby now the features in the data become magnified such that there's a now clear separation. And so there are a couple of
Wait.
ideas.
So when you say map it to a higher dimensional space, do you mean you add more predictors?
Say what?
Because
Okay. So what you do, for example, this data on your plot is a 2-dimensional, right?
yeah, I know. Yeah.
If I wanted to separate the blue points and the red circles, what I will do is then I define a mapping that takes each point, this is a 2-dimensional, into maybe a 5-dimensional plane. And then in that 5-dimensional plane,
I feel I got your idea. Yeah, that's what I was asking.
It becomes more magnified. Of course, how you do that mapping, it must be it's not very obvious, but there are such mappings, people develop them. And so, and now the nice thing is that you don't have to check all the data to decide where the decision boundary is. You only need to look at the ones that are closest to the decision boundary. And those are they're called the vectors. And so now the people have like vector machines to do the decision boundaries. And so how now this works out in quantum machine learning is that you have 2 methods to find that decision boundary. If you only care about the vectors, the points that are closest to the decision boundary, and you take them as the critical points, you can form what they call a kernel. And once you have the kernel, you basically, it's more like well, how can I relate it to? It's like once you in statistical mechanics, once you find the partition function, you're basically done, right? And so people, what they're doing is that they are classical methods to find the kernel, but usually, they are computationally taxing. And so what people are doing now is that, okay, we can map the kernel more efficiently into a quantum circuit. And so the idea of
Wait, what? Map to what?
into a quantum circuit. And so like into
What's the quantum circuit?
so a quantum circuit is what we use to run quantum algorithms on a quantum computer.
Okay, then I don't let me think about it.
Okay, sorry. But basically, it's the same as a convolutional neural network. You know, the whole subject of neural networks, they have a one-on-one mapping with the theory of quantum circuits. But in any case, it turns out it's much more efficient to do it on a quantum computer. Why? To find that kernel. And once you find that kernel, then you do the math, and it's more like you have the partition function now, and everything works out nice. And so these are very interesting things, because some of the computational complexities that our forefathers in physics were facing, we now have tools that we can overcome the challenges.
Oh yeah, certainly yes.
Yeah.
So do you work on this project as your like the thesis project or what?
No, but you know, I mean, we are scientists.
No, yeah, I agree. Yeah.
We have interest around the region, but we have a PhD to finish. But yeah, these ideas are certainly interesting, and it would have been nice to explore that. But yeah, I'm not using quantum machine learning in my project. I'm just using more. Basically, my project is you find more efficient ways to encode nuclear physics problems into a quantum computer, and then find efficient algorithms to solve that.
That already sounds pretty complicated.
It's not. It's just maybe so many things to learn, because you have to learn the nuclear physics and also learn the quantum computation.
Yeah.
And now build the bridge. Yeah. Okay. It looks like our 5 minutes is over. Are people done now? Is everyone done?
I'm done. I don't know.
Anyone else who needs more? Yeah, you can stop sharing, Kim. And
Okay.
anyone who needs more time? I'm assuming no one needs more time. Okay. Today I'm doing multiple things, and so forgive me. I will share the student opportunities, and then afterwards I'll then give an announcement of the results of today's winners, if that's okay with everyone. Okay, sounds good with everyone. Let me see. I only have 4 responses. Okay. Today is it's an interesting day. It's an interesting day. Okay, I have the results now. Okay, let me start sharing the student opportunities first. Okay. Yeah, so thank you for hanging in there. Oh, okay, student opportunities. The first slide is one that was very interesting to everyone. If you guys did not know, if you go to WMU Pantry, they are having a pilot program where you can get 5 meal tickets to go eat in the Valley Dining and Henry Grab and Go.
Oh, I would love that.
Yeah, so go there and apply and get your 5 tickets and enjoy.
Where should we go?
Huh?
Where should we go?
So go to WMU Pantry.
Okay.
Yeah. So then you can then click up, you scroll down, click apply, and then you'll be sorted. I thought everybody would enjoy this. Okay, so then there are postdoc opportunities. If those who are closer, you can check this one out, the National Academy of Education. And if you are an American, you can check out the Graduate Research Fellowship Program. And so I believe the deadline is coming up very soon in November as well. And also, I saw that this scholarship is also like borderline social sciences, so probably people in science education will benefit for this, but the deadline is coming up very soon. And correct me, Kushi, if I'm wrong on this. And I also checked the international dissertation. That's also borderline human sciences and connecting what we do in physics and maybe teaching and applying it in that realm. And also the other scholarships, the Soros Fellowship, the deadline is coming very soon. And also the Smithsonian's Fellowship, they have a lot of projects. Even you can find postdocs here. And so some of the projects they are working on could be classified as application of physics in other areas. And so check that one out and see what interests you. And also the women, you have a way of being empowered. So there is a scholarship for women in, so you can apply and get more out of that. Also have dissertation fellowships. Coming up very soon, this one, I think every grad student who's now doing their research should apply. You know, it's October 27, which is probably next week's Wednesday. So yeah, so you can apply. You can apply it for either a research grant or a travel grant, and you can get any combination of the 2-3 times in I think in lifetime here as a PhD student or something. But yeah, the grant is up to $1,000, and so do apply. And they also postdoc in Argonne if you're interested in that as an experimental physicist. Do check those one out, and they have what they need there, and the skills requirements. And so another thing I wanted to mention: how many are APS members here? If you're a member of APS, you can raise up your hand. I can't see everyone. Okay, so do sign up. If you go to APS and you go to careers in physics, you'll see a lot of things there. And they also, if you scroll down, you'll see they have information for if you are international students and getting a visa, a work visa, and all of those things. They are a very good resource. And so with that, thank you. It's now time for me to announce the winner. Are you guys excited? Is there any drum roll? So actually today it's quite interesting. The winner is a tie between Om and Dave. Oh wow. And they both got 40 out of 50. So that's like 4/5 of the questions. And so we'll give it to Om because Dave, you've been taking everything. And so congratulations, Om. And yeah, thank you everyone for participating. I hope this was look at Dave. You already won twice now. So I hope it was a good learning experience for everyone. And yeah, we'll meet up for the next one. Okay, thank you very much, Kin. Let's thank our speaker, Kin,
sure.
and everyone who was here.
Thanks, Kin. It was a good talk.
Yeah, thank you.
Okay, bye. Have a good day, guys.